when this is a continuation of lecture 11. This is lecture 11C. I want to give you a brief idea about composite design. And when you use materials such as composites in to make a component that is used in actual specific applications, it is not enough to just use the average or the mean properties. You have to develop a design allowable value based that is obtained from the basis value A or B, and the design allowable is an experimentally determined acceptable stress value for a material. It is called allowable stress, so you all probably know that, and it is a function of the material basis value, the layup, damage tolerance, open holes, and other factors. So how do you calculate the basis value A or B? That is based on, you have to numerically calculate that based on the average values and the standard deviation of a population of samples. And you also have to make sure that the critical stress is less than a proportion that is based on the margin of safety. So, you can have a margin of safety of 2.5 or 2 or whatever. And the interesting thing is that if you develop these properties based on only on, say, 10 strength tests or whatever, it's going to give you a lesser confidence. And you can either have a 90% reliability estimate or a 95% reliability estimate or a 99% reliability estimate. And we need to do that in a conservative fashion. So if you do it with a smaller number of samples, you are going to have a non-conservative design situation. So in order to prevent that, what you do is you have to have a tolerance limit on the percentile is recommended, and the MIL 17 handbook will describe that, and I will post that in your bibliography. So how do you calculate that? The B basis, most of the time we take B basis values as the for the design allowables, and we use that based on 90% of the data will exceed the basis value with a statistical confidence level of 95%. So you take the standard deviation, and one standard deviation is plus sigma, and your average 90% of that, you will say that your value should exceed that by at least one standard deviation value. And A basis value is more conservative, but you typically do not use that, and there we say that 99% of the data will exceed the basis value with a statistical confidence level of 95%. And how do you calculate the basis strength value? It is the mean strength minus a constant times the standard deviation. So in this case you would take it as constant would be 1 or something like that, 1 or you can say 2 standard deviations or 1 standard deviation. You do that and you calculate, and it is based on the number of data points and the assumed distribution of the data, whether it is normal distribution, Weibull, etc. Okay, so for the B basis values, typically you have to test at least 18 samples, and for the A basis value you have to test at least 55 samples, especially for composites. And if you make the components, if you make the samples in one shop and you are trying to say that you are using the same basic materials, same basic manufacturer, etc., and you are seeing if your batch is going to be similar to the B basis values, then you can probably test only 8 samples. I'm not sure that you understand what I'm talking about here, but those of you who are in the manufacturing group, like Alex, can probably understand what I'm talking about. Okay, so this design is driven by the lowest basis value for a given property over the operating temperature range. So for compression, this might be hot, wet. For tension, it might be cold, dry for a particular material. And so if you are using design under certain conditions, you have to do the testing for each condition. So 18 samples for each condition you have to do for B basis, for generating the B basis values, if you understand what I'm saying. Okay. So what are the issues of database generation? I mean, so for most metallic materials, it is pretty easy to obtain public domain databases. But for composite materials, these typically have been generated separately for each airframe manufacturer or aircraft program, and the data is considered proprietary. So no public domain data will exist. As a result, so each manufacturer has to generate, even if you use the same materials, you have to generate the same test data over and over and over again, because the manufacturers don't want to, I mean, the OEMs do not want to give up their design data, if you understand what I'm saying. So unfortunately, so that means that you have to use expensive testing, very costly qualification. So if you change anything, you have to go through this all over again. So the best way to address this would be to generate publicly shared databases. And the FAA and NASA initiated that in the 90s, but and they have been trying to do that, and most of the time this has been done by the National Institute for Aviation Research at Wichita State University. And the data is all based on basic laminar level. And this is being extended to other classes of materials and this thing. So they call it National Center for Advanced Material Performance. And they have been established to generate, publish, and maintain the public databases especially for out-of-autoclave type of materials. So what is the advantage of shared databases is that low cost qualification. So I've listed there what are the advantages. So please go through that and understand what I'm talking about. I will post some of these papers and lectures that will give you a better understanding of what we are talking about here. Okay. But the problem is that most of the databases are proprietary for each customer. So we don't know exactly how to overcome that issue. So American Composite Group, before they became Solvay, they initiated that in the case of out-of-autoclave type of materials. So I will stop here. I mean, there are several slides related to that, so I will let it be there. You can read through that. Okay, so there are several databases for out-of-autoclave type of material, so you can use that information and use it for your design applications. So if you have to do equivalency of this data at your location, what you have to do is you have to test at least 8 samples under each condition. And especially under certain circumstances, like if you need damage tolerance and things like that, you need to make sure that um, you accept more conservative values than what the averages that you are getting. So if your standard design practice is for a 6.35 millimeter hole, then you may have to use it for a smaller hole. Okay, or if you have notch strain, you may need to use a lower notch strength than more brittle, less damage tolerance systems. So in this case, you have to do things like you have to measure the properties after impact. So what you do is you don't test. I mean, if you are expecting materials to withstand low velocity impact, what you have to do is you have to put it into a fixture and you have to shoot, say, an aluminum ball, a small aluminum ball or whatever, and then you test it under fatigue. So that is typically called a compression strength after impact. So you need to look at that and see if your properties are going to be within that required limit or not. So here are some equations for similar stress concentration factors, etc. But so you have to do similar things for every single condition, every single test condition. Okay. Um, Switching gears a little bit, especially if you are looking at composite material systems at elevated temperatures beyond 350 degrees Fahrenheit, you have to start using what are called BMI or bismaleimide. We talked a little bit about that in the initial lectures, and so our Solvay or American Composites Group also has an out of autoclave BMI system. What we have done is we have made high temperature Warton for making BMI type of structures. So these guys have out of autoclave BMI systems which can be used for compression molding also. So similar properties, you have to measure the compression strength after impact, and you test it at different temperatures and so on. Okay, so I will probably stop here, and so this one shows some results with some of the trials, out of autoclave trials and things like that. So they have made, ACG has made several prepreg types with the BMI also. I believe that they have made it with other types of resins also, like cyanide esters and things like that, but those are still under development. Okay. And one of the applications is, so the BMI can go up to 400 degrees Fahrenheit. So you can use these materials for making tooling for graphite epoxy materials that need to be cured at 350 degrees F. So you can use BMI prepreg to make the tooling for molding graphite epoxy type of materials. Okay. So I have a small homework. This is number 10. So I know that I need to post or set up the areas where you need to upload the homeworks. I'll do that today here in a little while. I promise that. Anyway, so please look at that and look at a paper with out of autoclave processing, and describe in a couple of sentences why this processing method is important, and describe one application that is using this method extensively. And I would also like you to look at vacuum levels that are needed for out of autoclave processing. We did talk about that a little bit and how that can affect the final part properties. So please describe that in your homework solution. Okay, so that is about it, and I will stop right here. Thanks.